Okay, so now that I've started the recording, you can type your name into the chat and we'll have a record of your attendance. Hopefully more people will come in. So thank you very much for responding to my survey about times for next semester. Yeah, unfortunately, I can't do this time because I'm going to be teaching a Friday class at the university that meets at this time. So I have to move the time, but it looks like for almost everybody that the Thursday time, 4 to 6, also at the same time, is the best. And so that's when I'm going to be doing it. Okay, so I'll write it again on the WhatsApp chat, but Thursday to 4 to 6. We'll do Thursday 4 to 6 next semester, starting on January 23rd. Okay. Okay, so we'll have today's class and then one more class this semester, and then we'll have a holiday break. And then on January 23rd, we're going to restart again. Okay. So, great. Okay, so I hope everybody's doing well. So last week, if you remember, we did a lot of work about kind of the idea of the derivative. It was a very conceptual week. This week is going to be a little bit more about formulas. We're going to be deriving some formulas for how to work with everything. But as always, I like to start with a little review. We'll go over the homework, and I think some of the derivations this week are going to be a lot of fun. We're going to be proving some pretty serious results in calculus this week. That'll also be very useful results that we're going to use a lot over the next term. Okay. So let's just remind you before we even go over the homework or do anything, this definition of the derivative that has been kind of the main focus of this semester, right? So the derivative here encodes the common solution of both the tangent problem and the velocity problem, and it's given by definition by this limit, right? So if f of x is a function, then its derivative is the limit as h goes to 0 of f of x plus h minus f of x divided by h. And this is giving you the slope of the tangent line to the function at the point, to the function f of x at the point x. And we have all sorts of other standard notations for the derivative that we'll use here and there. So you can say d dx f of x, you can say dy dx, or you can say y prime if you have y equals f of x. All of these notations mean the same thing. They all mean the derivative. Okay, so I wanted to go over the problems from last week. So remember, the other thing that we did last week was we talked about taking a derivative, and then you can take a second derivative, and you can take a third derivative. You can do the derivatives of the derivatives. And we saw that, at least in physics, the second derivative had this interpretation as acceleration. If you started with a position function, then the first derivative was corresponded to the velocity, and the second derivative corresponded to the acceleration. Okay, so this was one of the applications we had of the second derivative. So the first homework exercise is this straightforward exercise. So we have f of x as a function is 2x squared minus 5x plus 8. Okay. Good afternoon. Welcome to everybody who's coming in. I'm glad everybody seems to have gotten their data now. So 2x squared minus 5x plus 8. And so what we want to do is calculate the first derivative, the second derivative, and the third derivative. And what these are is just taking a derivative. Okay, so Princeton, I see a map. So the first derivative is 4x minus 5. That's exactly right. Because the 2x squared becomes 4x, right? The 2 goes down over here, and it becomes a 1. And then here, the x just becomes 1. So we get a 5. And this is the constant, the 8. So the 8 becomes 0. Good. And so we get 4x plus 5. If we take another derivative, what do we get next? So the derivative of 4x plus 5 is just 4. Okay, so I see Princeton is just 4. Great. And then the third derivative for Princeton and Enoch, exactly right. The third derivative is 0, right? And this is what happens with derivatives of polynomials, at least, each time we take a derivative, because of the power rule, we go down 1 degree. So it goes from a quadratic polynomial to a linear polynomial, and then down to a constant polynomial. And then once you have a constant polynomial and take another derivative, then you end up here at 0. Okay? So this is how we find all of the derivatives of this function. And I should just recall, if maybe people's connection wasn't so good, I'll just recall the power rule, which says that the derivative of x to the n is equal to n x to the n minus 1. Okay? So this is the rule that we're using to differentiate this function and then to differentiate it again. All right, any questions on this example? Oh, okay, if it's fine, let's move on.
Yeah,
Oh, yes,
hello.
question? Yes, Enoch?
Yeah, it's the last time you talked about proving the derivative if you have the function to be s raised to the power n to prove it to have n times l raised to the power n minus 1.
Mm-hmm.
Yeah,
Yeah,
so
we're not.
I actually
Mhm.
I actually did then, but I'm not at my house now. I came somewhere, so I left it with my assignment and the proofing. I did it. I also submit my assignment, but since 4 days now, I'm not to my house.
Okay, so just whenever you get back to your house, you can send it to me.
Okay, okay.
Okay, thanks. Okay, so that's the first problem, pretty straightforward. Okay, so for the second problem, we have a physics problem, right? So a ball is thrown vertically upward with an initial velocity of 80 feet per second, and its height after t seconds is given by f of t equals 80t minus 16t squared. Okay, so this is a height in feet. So what is the maximum height that it reaches? Okay, and the hint is, what is its velocity when it reaches the maximum height? And then we use this to figure out the time and the position. So let's answer that first question. So what is the velocity at the maximum height? Right? We have a ball that's going up. It goes up to the top, and then it goes back down, right? This is how the ball gets thrown. So when the ball is right there at the top, what is its velocity? Right? The velocity is upwards, and then it becomes downward, and in the middle, it gets to this point right at the top of its arc. And so what's the velocity of the ball at the top of the arc there? So this is just as a preliminary question. Well, the key observation right here is that when you're at the top, right, the velocity is equal to 0 when you're right at the top. Because at the point where the ball gets to the top, it's not moving up and it's not moving down, right? It goes up, it's got an upward velocity. The upward velocity gets slower and slower and slower. And then when the ball gets to the top, the upward velocity is gone, it vanishes. And then it starts falling, and it starts falling faster and faster and faster and faster as it falls. But at that moment, when it's right at the top, the velocity is 0. Okay, and so this is a key thing. Anytime you have a continuous motion, whenever the direction is changing, you go from one way to going back the other way, the velocity is always 0 at that point where everything changes. So the velocity is 0 at the maximum height. So let's do the velocity function. So f of t here is the position function. So the velocity function we know is given by the derivative of the position function. So the velocity function is f prime of t. so if f of t is 80t minus 16t squared, the velocity function is going to be 80 minus 32t,
Yeah.
right? 32t, right? Because it's the derivative of this. So we want to solve, if we want the velocity to be equal to 0, we want to figure out what time that is. So we solve for t in 80
So
minus 32t equals 0.
yeah, sure.
Yeah, so what's the solution there?
Yeah, so you will have 32t equal negative 80.
hmm
Then you divide both sides by 32, you divide the other side by 32.
hmm Great. So we can move the 32t on the other side. We get 80 equals 32t. And this leads to t equals 80 over 32, which simplifies to 2.5. Okay, yeah, 5 halves. Great. So great.
Yeah.
So 2.5. So this has happened when we solve for t. So t equals 2.5 at the top of the arc. So now let's remember, what does the question ask, right? The question says, what is the maximum height, right? So we have kind of three steps. We have one, what is the velocity at the maximum height? Two, this gives us that, t equals 2.5 at the maximum height. And now we have three, what is the maximum height? Well, we have to plug our time into the height function, right? This is the height function, is f of t. So we have to actually evaluate f at the time where it reaches its maximum height. That means we
Yes.
have to
Hello,
actually
please.
evaluate. Yes, Princeton?
Yeah, please. Yeah. So
Yep.
to find the max, we say f of t, which will be equal to 80 t minus 16 t squared. So
Mm-hmm.
we replace the t now with 2.5.
Mm-hmm.
We're going to say 2.80 times 2.5 minus 16.
Mm-hmm.
So it will be 2.5 squared.
Right.
So we multiply the 80 by 2.5, it will get 200.
Mm-hmm.
And then we take the square root of 2.5, it will give you like 6.25 and multiply by 16, it give you 100. So we
Mm-hmm.
subtract the 100 from 200, we give you 100 as the maximum
Yep.
height.
Great.
F of t, right?
Right. So this is goes pretty high, throwing a ball 100 feet into the air, right? So it tells you that throwing a ball at 80 feet per second is pretty difficult because 100 feet, it's like 30 meters. It's very, very high to throw a ball into the air. So you'd have to be pretty strong to do an initial velocity of 80 feet per second. Um, but yeah, this is exactly right. And so we end up with 100 feet. Okay? So this is a three-step problem here. You first have to realize that the velocity at the maximum height is equal to 0. Then the second step is where you actually use calculus, right? The second step is when you're solving for what is the time at the maximum height by using that the velocity is 0 and setting 0 equal to the derivative. This is going to be similar to what we do next week. But we take the derivative, which is the velocity function, we set it equal to 0. That gives us that the time is 2.5. And then the last step, we just punch in 2.5 to figure out what the height should be. Okay, any questions here? Okay, great. Okay, so we get 100 feet there. Okay, exercise 3. So we have a dead rechargeable battery plugged into a charger, and the function c of t represents the percentage of the charge recovered after being plugged in for t hours. So let me say here's c of t, and this is t, and this is going to be 100%, and this starts off at 0, and the function is going to look kind of like this. Okay, I'm going to do this here. So here is the graph of C of t. And so what we want to do, and let's just say, right, so the question, so there's two parts of this question. So first we want to sketch a graph of C prime of t. We want to sketch a graph of the derivative based on this graph over here. So remember what happens when the battery gets charged, it's recovering, and as it gets close to full power, it starts recovering slower and slower. It never quite gets all the way to full power. This is what's called a horizontal asymptote. But it keeps recovering more charge, but very, very, very slowly once it's almost full. So in red, let's draw a graph of the derivative, and let's draw it on the same axes. So we're going to have this same time axis over here. But what we want to know is the derivative starts out as this slope, right? The derivative at any point gives the slope of the tangent line. And as the graph flattens out, let's just draw a couple of representative tangent lines over here. So this might be what the tangent line looks like here, but this is what the tangent line looks like here. And this is what the tangent line looks like here, right? The slope is getting smaller and smaller each time. Right? So if we want to, so if this blue here is, y equals C of t, maybe I won't call this C of t. I'll call this percent charge. Okay. So if this is C of t, then in red, what's really going on here? It starts by recovering the charge very rapidly, and then as time goes on, the charge is recovered more and more slowly. So what actually this should look like, the derivative, is we start, pretty high, some number. I can't tell exactly what it is because I haven't given you the units for t, or I haven't labeled the units for t on the axis. But at least schematically, we're going to start by recovering the charge pretty quickly. We've got a slope over here, whatever that is. And then we're going to go, it's going to get slower and slower. So it's going to go down like this. Oh, wait, no, I wanted to do that in red. Hold on. Do that in red. It's going to start recovering slower and slower, which means, so this is C prime of t.
Yes.
And the idea is that C prime is the slope of the tangent line here. That's getting closer and closer to zero as t moves on. So this over here is going to get closer and closer to zero. It's never getting negative because we're always recovering a little bit of charge. But as the battery gets almost full, then the rate at which you're recovering charge gets very, very slow. So it goes down to zero. Yes, is there a question?
Yes, Dr. Obus.
Yeah, Princeton?
So that means the graph are very decreasing, right?
Yeah, the graph of C prime is decreasing.
Yes,
because the rate is, because you start off recovering very quickly, and by the end, you're recovering much more slowly.
So that means the value for t now will be increasing in this case?
Yeah.
Okay.
Right, because if C is increasing, that means that the slope is positive. And so C being increasing is the same as C prime being positive. Right, we'll talk about this a little bit more next semester. But the point is, right, if C is increasing, then C prime is positive. But C prime here is some very small positive number, which means C is increasing very slowly. When we're almost at full charge, we increase very slowly. Okay, and so what's the meaning of C prime of t? Can anybody tell me in words, what the meaning of C prime of t is here? So for this, we have to remember what a derivative means, right? I mean, a derivative solves some problems. It solves this tangent line problem, and it solves the velocity problem. But in general, what a derivative represents always is a rate of change. So c prime of t, this is a function. You plug in some time and you get some number. What does that number mean? Meaning of c prime of t is it's the rate of change of the battery charge at time t. And we have to say what this is measured in. This is measured in percentage of full charge recovered per hour, right? Because here t is measured in hours, and our y-axis over here is the percentage of the full charge. So if c prime of t is equal to 50, that means that we're at a rate of recovering 50% of the full charge per hour. Okay. Okay, if c prime of t is 10, which maybe it is when we're very close to the end of the charge, we're saying that we're recovering about 10% of the total charge per hour. Okay, so it's a rate. The derivative, when you're talking about a function of time, the derivative is always a rate of change. Okay, and it's how much your y-axis value, in this case percentage of the charge, how much that is changing per unit of time on the t-axis or the x-axis. So in this case, it's the percentage of the full charge recovered per hour. And so that percentage starts out really fast, but it rapidly gets slower as the battery charges fully. And by the end, you're recovering very small percentages of the full charge per hour. Okay, any questions on this?
Yeah, that
Yes,
this
question.
issue about the rate of change. I'm a little bit lost between the rate of change and the which coefficient selection will give us the change in C.
Right. So, I mean, again, I haven't written any actual equations here, any actual formulas. But if you mean which, so imagine, so maybe this will help. So imagine in 1 second we recover, let's say, 0.01% of the full charge. Okay, let's imagine that we do that. So like in 1 second, we recover 0.01% of the full charge. So what is that as a rate of change over here? We can think of 1 second as being a very small time interval. So this is almost the instantaneous rate of change, right? And so what is this? This is 0.01% per second. I'm sorry for the writing being so small, but we want to change this into hours, right? So we have to multiply by 3,600 seconds over 1 hour. Is how many seconds are in an hour. And what this comes out to be is 36% per hour. So for instance, if you're recovering charge where you recover 0.1% of the full charge in 1 second, as a rate here, that's 36% of the total charge per hour. And so in this case, that would mean that C prime of t would be equal to 36. Those would be our units here. Okay, so whatever your instantaneous rate of change is, and you can approximate that pretty well by seeing, how much charge is recovered in 1 second. You can do that, you can extrapolate that to an hourly recovery, and that's going to be your C prime of t. So in this case, if you were at a time in your charge where in 1 second you recover 0.01% of the full charge, then at that point C prime of t would be equal to 36. Okay, is that helpful?
Yes.
Okay,
I get it.
all right. Any other questions? Okay. All right, so let's move on to what we're going to do for today, which is going to be much more about formulas, a little bit less about conceptual stuff and more about formulas. So I want to recall these rules that we have for taking derivatives, right? So these are rules that we've done for the last 2 sessions. So the most important rule is this power rule. If f of x is x to the n for any real number n, then f prime of x is n x to the n minus 1. Then we have these other 2 rules that we already used in the homework, which is the constant multiple rule. Basically, if you multiply a function by a constant, then the derivative gets multiplied by the same constant. And and then we also have this addition and subtraction rule, which is that if we add or subtract 2 functions and take the derivative, the way we do that is by taking the derivatives of each of the 2 functions and adding and subtracting them. Okay, so the derivative of the sum is the sum of the derivatives. But this works for plus and for minus, but what we saw last week is that this does not work for times. If I have a function that's given by multiplying 2 functions, f and g, so if h is f of x times g of x, then the derivative of h is not the same thing as the derivative of f times the derivative of g. 1 second. Great. Okay. So this is not equal to, and so we want to know if I have a function that is a product of 2 functions, what is the derivative equal to? And so the answer to that is the product rule. Okay? So what we're going to do, we're going to calculate that today. So let's suppose that h of x is f of x times g of x, and I want to calculate h prime of x using the definition of the derivative. So let's do that, right? So h prime of x is equal to, by definition, we know that it's the limit as, I already have this letter h. Let me not use h. Let's say it's the limit as z approaches 0 of f of x plus z minus f of x over z. I'm just using a different letter so that because I already have the function h over here. Oh, sorry. So h of x plus z minus h of x over z. Right? This is just the derivative formula with a z instead of an h. And what this means, well, h is the product of f and g. So this is f of x plus z times g of x plus z minus f of x times g of x divided by z. Right? I guess I should write the limit again. I should write the limit again. So this is the limit as z approaches 0 of this. Okay. Okay. So, okay. So how do we evaluate this limit, right? Again, I can't just punch in z equals 0 because I just get f of x g of x minus f of x g of x over z. That's just going to be 0 over 0. So here we have to do a little trick. So here's the trick which makes this work. I'm going to take f of x plus z, g of x plus z, and now I'm going to subtract f of x plus z times g of x, and then I'm going to add f of x plus z times g of x. I'm allowed to do that. I can always add and subtract the same thing. And then I'm going to subtract f of x times g of x. And this whole thing, sorry, I keep forgetting to write the limit. This is the limit as z approaches 0 of this whole thing here over z. Okay, so all I did was add and subtract the same equal thing, right? So I'm certainly allowed to do that. So why did I do that? Well, now let me break up this limit into 2 pieces. So this is now the limit as z approaches 0 of f of x plus z, g of x plus z, minus f of x plus z, g of x over z. That's one piece, plus the limit as z goes to 0 of f of x plus z g of x minus f of x g of x, all divided by z. Okay, so I have two limits here that I get by I start with my definition of the derivative, I write what that means, and then I subtract and add the same thing, and that lets me write these two limits. And what's nice about this is that I have here an f of x plus z, right? Which I can just take out, right? So this is equal to the limit as z approaches 0. I can write this as f of x plus z, that factors out, times g of x plus z minus g of x over z, right? I'm just rewriting this by factoring out a factor of f of x plus z. I have that in the numerator. And similarly, I can take the limit as z approaches 0. Here I have a g of x that I can factor out. So I get here g of x times f of x plus z minus f of x over z. All right, so let's now do all these limits. So as z approaches 0, what does f of x plus z go to? Well, as z goes to 0, this just becomes f of x. Over here, what does g of x plus z minus g of x over z go to? Well, this thing is just the formula for the derivative of g, right? This is just the formula for the derivative of g. So this is g prime of x here. Now here, g of x is just g of x. There's no z in it at all. And then over here, I have f of x plus z minus f of x over z, limit as z goes to 0. That is the same thing as just the formula for the derivative of f, right? So this is f prime of x. Okay? So when we sum it all up, we get that h prime of x, the derivative of h, is equal to f of x times g prime of x plus g of x times f prime of x. Okay? And this is what we call the product rule. Okay, so by the way, in terms of sections, this is all from section 2.4 of the book. Let me make sure. This is all section 2.4 of the book, yes. Okay, so we have to do some complicated algebra over here, and you need this special trick where you just have to have this inspiration to subtract and add the same thing in order to evaluate this, limit. But once you do that and you break the limit up, you just have to break the limit up into pieces, and these pieces are straightforward, and these other pieces you just recognize, like, I know what that limit is. That is just the derivative. And so it all simplifies down to a formula that's pretty easy to remember, okay? So h prime of x is not just f prime of x times g prime of x. Instead, it's given by f of x times g prime of x plus g of x times f prime of x. Okay, and so this is what's called the product rule. And we can use this to evaluate derivatives. So here I'm just repeating this. So this says the product rule. If h of x is f of x times g of x, where f and g are differentiable functions, then h prime of x is, oh, that shouldn't be an equals, that should be a plus. Then h of x is equal to f of x times g prime of x plus f prime of x times g of x. Okay, this is the same formula that I wrote on the sheet last time. So let's check this. Maybe I'll call this h of x just to check. So let's check this in the case where h of x is equal to, I can write it as x squared plus 2 times x plus 3. And if you multiply this all out using FOIL, this turns out to be x cubed plus 3x squared plus 2x plus 6. So what does it check? Well, we'll use the product rule, which says that h prime of x is equal to, well, what is that? The first times the derivative of the second plus the derivative of the first times the second. So the first times the derivative of the second that's x squared plus 2 times the derivative of x plus 3, which is just 1, right? That's the derivative of x plus 3. And then plus the derivative of the first, the derivative of x plus 2, which is 2x, times x plus 3. So plus 2x times x plus 3, right? Here, if this is f and this is g, we have that this here is f, this is g prime, this is f prime, and this is g, right? That's how we're writing them all down. And then if we simplify this, this becomes x squared plus 2 plus 2x squared plus 6x. Or in other words, it simplifies to 3x squared plus 6x plus 2. Okay? And now we check that this is actually right. Well, we know that this product is equal to this polynomial. We should take the derivative of this polynomial. We should get the same answer if the product rule is right. Well, let's check by
Yes,
taking the derivative of this. Yes, sorry, question?
yes. I have a
Yes,
question
Princeton.
where we have s squared plus 2 plus 2s squared plus 6s.
Mm-hmm. Yep.
Now, we got s squared and 2 plus 2s squared. How can we get 3s squared? Go get
Well,
s squared plus 2s squared. So,
I think that is
right.
just direct multiplication
I'm
and
just doing the
addition.
multiplication out here, right? So this is just the 2x is getting multiplied by the x and by the 3.
yeah, I get it that, but I'll talk about the second equation here where it say all equal to s squared plus 2s squared. I think we bring the 2s squared and the s squared together.
Right. Yeah. So
And
yeah,
give us the 3.
that's right. So
Yeah.
the 3x
Then how
squared
can
is
we get
coming
3?
from, well, it's just the x squared plus the 2x squared is
Oh,
3x squared. I'm just
okay.
combining those two terms.
It's to evaluate whether our derivative will be equal to the equations to the next equation. That's what going on.
Okay, I
Right.
understand. I understand.
Right. So now we're
Okay.
right. So
Thank
we
you.
do this check. We now say this should just be the answer. Let's see what is the derivative of x cubed plus 3x squared plus 2x plus 6. If we just do this using the power rule, we get 3x squared. That's the x cubed. And then 3x squared becomes 2 times 3x, which is
Yes,
6x, and then plus 2. Great. And the 6 becomes 0, right? So what we see here is we have that what we get from multiplying out and taking the derivative, is the same as what we get from using the power rule. So this is a confirmation that the power rule works here, right? We calculated this derivative two different ways. First, by multiplying out and taking the derivative. Well, no, first by using the power rule, and second by multiplying out and taking the derivative. And if the power rule is correct, which it is, we should get the same answer, right? And that's exactly what
So
happens here. We get the
Dr.
same
Obus,
answer. Yep.
Dr. Obus,
Yes.
somebody will ask if I prefer the derivative to be used instead of the power rule,
Yeah.
instead of the product rule.
That is fine. But we're going to see examples later on where you have to use the power rule, where you won't be able to do it
Okay.
otherwise. Yeah. So for this example, you could do it either way. We're just checking that the power rule works. But we're going to see examples today where you can't use the power rule. Okay. But for at least this is a good confirmation that our formula gives the right answer, even if it's not the way that you want to do it. All right. Any questions on this? Alexander?
But I think that the power rule actually help to really help you to verify actually whether your derivative works
Mhm.
perfectly.
Yeah,
Yes. So
exactly.
using always mastering the power rule helps you in every form of derivative because it helps to counter check whether there are mistakes or issues along the way while you're doing the direct derivative. So it helps a lot. So I even prefer using the power rule than to go directly to the derivative. Because
Yes.
derivative is just something in the mind and you're going to be applying it. But the power rule will go from one step to another and we should be more detailed than the derivative directly. Thank you.
Right. You're welcome. So that works as long as you've got a polynomial. So the point is later today, we're going to be doing trig functions. And then once you're doing trigonometry
Yeah.
functions, then you can't use the power rule
Yes,
anymore.
sir.
Yes.
Very
Yes, sir.
complicated at that point.
Yeah,
Yeah,
Prince?
thank you so much for Thanks. Thank
Yeah.
you so much for this explanation and then solving of this equation or the problems. My concern have been due to this plan. Really, I have a little bit, confusing mind when it comes to when he's speaking of prime, H prime, F prime, G prime. What does
Hmm.
that really mean?
It means the
Yeah.
derivative, right? So f prime is just shorthand for f prime of x, and g prime is just shorthand for g prime of x. So if you want, I could write these as g prime of x, f prime of x, and g of x. It's just shorthand, not including the x. So this just means the
Okay,
derivative
okay,
of g, and this just means the derivative of f. So here the derivative of g
okay.
is 1. That's why we get a 1 here. And here the derivative of f is 2x. That's why we get a 2x here.
So it definitely it tells us whatsoever we find, it will say f of x. It means whatsoever we find f of x, it should be replaced with g of x for it to be the prime of it.
Right. Well, I mean, you replace it with the derivative, right? So we're saying that if h is a product of f and g, then the way you take the derivative of h is by leaving one alone and multiplying it by the derivative of the other one. That's f of x times g prime of x. And then you take the derivative of the first one and multiply it by the second one. And so that's what's
Okay,
going on
okay,
in this example here.
okay.
Is
Thank you
that
so
okay?
much, sir.
Okay, you're welcome.
Yeah. It's a little bit honestly.
Okay. Other questions? Okay. Okay. So that's great for products. We'll get more practice with the product rule later. But what about quotients? So let's say that we have a quotient, right? So h of x is f of x over g of x, where g of x is not equal to 0. And so the question is, what can we get a formula for a quotient? Okay. Well, let's see. Again, we're just going to use the definition of the derivative and see what we get, right? So h prime of x, by definition, is the limit as z goes to 0 of h of x plus z minus h of x divided by z. And now it's going to get a little more complicated because h is a quotient, so we're going to get a complex fraction here, right? H is f divided by g. So we have the limit as z approaches 0 of f of x plus z over g of x plus z minus f of x over g of x divided by z. And in fact, if you simplify this all, I'm not going to do every step, but if you simplify everything here, it's going to turn out to be the limit as z approaches 0 of f of x plus z times g of x, this is getting a common denominator, minus f of x times g of x plus z, divided by g of x plus z, g of x, and z. Okay, I'm gonna leave this as exercise to show that this algebraic expression here simplifies to this expression over here. Okay, you have to get a common denominator here and then make it into a simple fraction. But maybe I'd rather. Oh, question. Yes, Rush. Question.
Hello?
Yes. Hi, Rush.
Yeah, I heard you saying that not all cases the product can and you can use the power rules. So
Right.
yeah, can I see one other example at least to understand?
Yes,
And
we're gonna do that next. So
okay,
later
okay,
on, we're gonna do the derivative of sine of x, which we can't
okay,
use the
okay,
power rule for. Yeah. So coming up
okay,
in a little bit.
okay.
Okay. So Harrison. I mean, okay, I can do this. I'll add an extra step here. So this is the limit as z approaches 0. Common denominator here would be f of x plus z times g of x over g of x plus z, g of x, minus f of x, g of x plus z over g of x plus z, g of x, and this whole thing over z, right? This is just getting a common denominator, so I'm multiplying by g of x over g of x here, and I'm multiplying by g of x plus z over g of x plus z here. That gives me this, and then when I combine these two fractions and make it into a simple fraction by just taking the denominator and multiplying it by z, then this ends up giving me this expression over here. Okay. So we get this expression for the limit. It's a little bit complicated. Okay, you're welcome. So now we do the same trick we did with the product rule. We're going to add f of x times g of x and subtract f of x times g of x. Kind of a magic trick that makes this work. So I'm going to say we have f of x plus z times g of x. This we have before. Now I'm going to add and subtract the same thing, so I don't change the value at all. So I'll just say minus f of x g of x, and then plus f of x g of x. And then we have a minus f of x times g of x plus z. And then this whole denominator here is g of x plus z, g of x, z. And all that I did here from the previous step was I subtracted f of x times g of x, and then I added f of x times g of x. That's the only change. Otherwise, everything carries over from the previous step. Okay. And now the advantage of this is we can again rewrite this as a sum of two different limits, or actually as a difference of two different limits. So this is going to be the limit as z approaches 0 of f of x plus z, g of x, minus f of x, g of x, divided by g of x plus z, g of x, z. And then we subtract the limit, or maybe I'll say we add the limit as z approaches 0 of f of x, g of x, minus f of x, g of x plus z, divided by g of x plus z, g of x, z. Okay, all I did here was split it up into two pieces. Okay, one piece for these two terms and one piece for these two terms. So you bear with me now, we're almost done. All right, so here I have a common factor, g of x. And here I have a common factor, f of x. And both of those cases, I can just pull that factor out of the limit because there's no z involved, right? It's just g of x, and this is a limit only as z goes to 0. So if I have something in terms of x, I can just pull it out. So this is equal to g of x times the limit as z approaches 0 of f of x plus z minus f of x over g of, let me even change that. This is even better. So in this one, I can just cancel out g of x from the numerator and the denominator. And so you know what? I can do that, but I don't want to. Sorry. Let me do what I started doing. So this is equal to g of x times the limit as z goes to 0 of f of x plus z minus f of x over g of x plus z, g of x, z. And this over here, I can do the same thing with f of x. I pull out f of x times the limit as z approaches 0 of g of x minus g of x plus z over g of x plus z, g of x, z. Okay, so all that I've done is pull out a factor of g of x here, and I pulled out a factor of f of x here. Okay, so let me try. I wish I had a little bit more space. I don't want to go to a new sheet because I don't want to completely You know what? Maybe I'll copy this down on another sheet, okay? Because I don't want to write too small. So let me copy this down on another sheet. We're almost done. So I'm just gonna recopy this down. Okay, so this is um, g of x times the limit as x approaches as z approaches zero of f of x plus z minus f of x divided by g of x plus z, g of x, z, and then plus f of x times the limit as z approaches zero of g of x minus g of x plus z over g of x plus z, g of x, z. Okay, all I did was copy the line from before. Okay, I copied it verbatim. This is the same thing. And so now here's where we have to see, well, this thing over here, f of x plus z minus f of x over z, the limit as z goes to zero of that, this is just the definition of the derivative of x, right? So this thing is just going to give me f prime of x. And likewise, g of x minus g of x plus z over z, well, it's not quite the definition of the derivative of g. The derivative of g would be g of x plus z minus g of x over z. Instead, the subtraction is reversed, so it's actually negative, but it's almost the same, it's just negative. So this is equal to negative g prime of x with these limits. So what we actually get when we simplify this all out is we get g of x f prime of x times the limit as z goes to 0 of 1 over g of x plus z, g of x. And then minus f of x, g prime of x, limit as z goes to 0 of 1 over the same thing, g of x plus z, g of x. And now what is the limit as z goes to 0 of 1 over g of x plus z, g of x? Well, as z goes to 0, x plus z just becomes x. So this is just 1 over g of x squared. And the same thing over here. So this is equal to g of x, f prime of x, times 1 over g of x squared, minus f of x, g prime of x, times 1 over g of x squared. And if we want to simplify the whole thing, because we've got 1 over g of x squared, we can make that a common factor, and this actually becomes g of x times f prime of x minus f of x, g prime of x, all times 1 over g of x squared. And usually we write this as a fraction, so this becomes g of x, f prime of x, minus f of x, g prime of x, all divided by g of x squared. And this is the final formula. And so this proof is pretty hard, right? You have to do a lot of algebra. But in the end, you're just taking a limit, doing a whole bunch of algebra, doing some tricks here and there, and you end up with this formula, which is a little bit harder than the product rule formula. Okay, so but this is the formula for the quotient rule. So if you have a function that's given by f divided by g, then its derivative is actually given by this formula. It's g of x, f prime of x, minus f of x, g prime of x, divided by g of x squared. And this is the formula that we call the quotient rule. Okay, so we have the product and the quotient rule over here. Okay, and the product formula is a little bit easier. It's just the numerator here, but with a plus instead of a minus. The quotient rule, you have to remember that there's a minus and there's this extra g of x squared there in the denominator. So notice this is definitely not just f prime of x over g prime of x. It's not that simple. It's a little bit harder. So on this next slide, I just have this rewritten nicely. So this is just repeating the formula. So if h of x is equal to f of x over g of x, where f and g are differentiable functions, then h prime of x is given by this formula. G of x, f prime of x minus f of x, g prime of x over g of x squared. Or if you want to think of it as shorthand, which is maybe easier to memorize, shorthand, you can say gf prime minus fg prime over g squared. Okay, that's maybe a shorter way to remember it. Okay, so let's check this. Let's check this. Let's evaluate the derivative of 1 over x using this formula. Right, so if h of x is 1 over x, we have that f of x is equal to 1 and g of x is equal to x, right? That's f of x is the numerator and g of x is the denominator. So we have that h prime of x is equal to g of x f prime of x minus f of x g prime of x divided by g prime of x squared. This is just the formula. So let's write down what this actually is. Well, g of x is x. So it's x. F prime of x, well, f of x is 1, so f prime of x is 0, right? Because 1 is just a constant. So x times 0 minus f of x, which is 1, times g prime of x. Well, g prime of x, g of x is x, so g prime of x is the derivative. That's just 1, the derivative of x. And then divided by, oh, sorry, that's not g prime of x squared. That's just g of x squared. Divided by g of x squared. Well, g of x is x, so g of x squared is just going to be x squared. And this simplifies to minus 1 over x squared. Okay, so the derivative of 1 over x, using the quotient rule here, is going to be minus 1 over x squared. Okay. Now we can check this also using the power rule. It's not really a check because we haven't proven the power rule for negative exponents. But keep in mind here that h of x is 1 over x. We can also rewrite that as x to the minus 1. If we check with power rule, that means that h prime of x is going to be minus 1 times x to the minus 2, which is equal to negative x to the minus 2. And x to the minus 2 we know is 1 over x to the 2. Right? So turns out, again, we get the exact same answer as we would like. Okay, so regardless of which way you do it, right, you can do it using the quotient rule, or in this case, you can do it using the power rule also. And in both cases, you get the same answer. You get minus 1 over x squared. Okay? So this quotient rule is a little bit harder to memorize than the power rule. Just means you have to do a few more practice examples, and then you'll be able to learn it. But in applying it, it's pretty straightforward. You just have to know what is your f, what is your g. You have a formula, and then you just figure out what each part of your formula means. And in this example, for instance, we'll do a second example. But in this example, it simplifies down to minus 1 over x squared. That's the derivative of 1 over x. And that agrees with what we would get by using the power rule here. Right, any questions on this example or on the quotient rule formula? I know the proof maybe went a little fast. You can go back and look at the proof on YouTube or on the notes that I send out, or in the textbook. It's in the textbook also. I didn't want to spend too much time on the proof, but I wanted to do it just to show you that this is not magic. This isn't just something that somebody said. This comes from actually trying to evaluate the limit of what this h prime is. Any questions on this example? Okay, let's do another example. So let's find the derivative of x plus 3 divided by 2x squared minus 5x plus 10. So note that for something like this, we cannot use the power rule. Right? This does not simplify to something that you can just apply the power rule to. This is not a polynomial, and it's not even some sum of, x is raised to some powers times some coefficients, right? This is a rational function, and the only way to take the derivative is to use the quotient rule. I'm just going to recall the formula again, right? If h of x equals f of x over g of x, then h prime of x is equal to g prime of x f of x minus f prime of x g of x divided by g of x squared. Okay, I'm just repeating the formula. So in this case, we have f of x is equal to x plus 3. It's the numerator. G of x equals 2x squared minus 5x plus 10. Right, we just have the numerator. And this here's the denominator. Okay. And so we apply the formula, right? So the derivative of x plus 3 divided by 2x squared minus 5x plus 10, we just have to apply the formula. So the derivative of g, that's going to be 4x minus 5. So 4x minus 5 times f of x, that's x plus 3. And then minus the derivative of f, so that's just 1. The derivative of x plus 3 is 1, times g, which is 2x squared minus 5x plus 10. And all that divided by the square, 2x squared plus 5x minus 5x. 2x squared minus 5x plus 10 squared. And that's it. Right? This is the answer. You can simplify it, but I don't want to simplify it. I mean, you can simplify it if you want to, but it'll take some time.
Hello.
For now, maybe I won't simplify. Yes, Rush.
Yeah, I don't know. I try simplifying about like what a god was. I don't know.
It doesn't simplify nicely. You can't cancel out any factors.
Okay.
Yeah, it's not supposed to. I mean, you can rewrite this as just some quadratic polynomial in the numerator, but then you're done. There's nothing you can do to cancel out.
Okay.
Okay. Yeah. So this is just what it is. It's not a particularly nice formula. I mean, this is not a particularly nice function. But if you use the quotient rule to take the derivative, this is what you get. And if you want, I'll just write that down. So if you're looking at your notes later, if you want, you can simplify the numerator. Okay.
So I want to ask a question.
Yes, question.
All right. The formula you said is g prime of x and f of x, right? Minus f prime of x, g of x, or g of x squared, right?
Mm-hmm. Yeah.
Because I don't know what are if almost is because what are the first one was I don't know g of x, f prime of x, right?
Sorry, so you mean for the product rule?
For the quotient.
Oh, for the quotient rule, yeah. Yeah, so this is it.
But we're seeing
Oh, did
something
I
like
mess it up? Hold on, did I make a mistake here? Oh, I made a mistake. Sorry. I made a mistake. You were right. Sorry. This should be reversed. Oh no, I'm sorry. Let me fix this. I copied it down wrong. G of x, f prime of x, minus f of x, g prime of x. And that means this actually has to be reversed. Sorry about this. So we have g of x is 2x squared minus 5x plus 10 times f prime of x, which is 1, and then minus f of x, which is x plus 3, times g prime of x, which is 4x minus 5. Right, so let me even label these to be careful. This is g, this is f prime, this is f, and this is G prime. Okay, thank you for catching that. I got the negative of what the answer was supposed to be. Okay.
So the answer I try to simplify, I guess something I don't know what I'll call it. 2x squared minus 22x plus 45, all divided by 2x, parenthesis open, 2x squared minus 5x plus 10 equals to all squared.
Right, but I think you have to negate that numerator, right? So it should be probably negative 2x squared. And then what's the x? You're going to have a minus 5x here, and you're going to have minus 12x here, and then plus 5x. So yeah, so it's going to be negative 2x squared plus 22x, and then you're going to have plus 15, so plus 25, right? Divided by 2x squared minus 5x plus 10 squared. Yeah, and this just nothing's going to get better. This is the most you can simplify.
Well, negatives, we have the negative, multiply the negatives by the other one, right?
Mm-hmm. Yeah,
Yes.
so this negative, right, we get a negative 4x squared, and then we get a negative 12x and a positive 5x here, right?
Yeah, so it gives you.
Oh, sorry. Did I made another mistake here? I'm trying to do this in my head. I'm trying to do it too fast. This is not right, right? We have a minus, oh wait, yes, yeah, so we have a minus 12x and then a plus 5x and a minus 5x. So, right, so shouldn't it actually just be, this should actually just be minus 12x, right?
Yeah.
Yeah, okay, thanks.
So that's negative, right?
Yeah. Yeah, so negative 12x. Yeah.
Yeah.
Okay, this is right. And then plus 25. Good. Sorry. Again, yeah, one could do this. Apologies for all the mistakes here. Okay. Okay, so this is another example of using the quotient rule. Any questions on this? There'll be another example on the homework to practice.
Yeah, sir.
Yeah. Question, Prince?
Yeah, my question have been due to this negative sign in the center. Now, this negative, is it affecting the x plus 3 or it affecting all, which is x plus 3 and 4x minus 5?
The mechanism, I don't know, right. So the x plus 3 here is the f, and the 4x minus 5 is the g prime, right? So they have to be multiplied together in order to get this term here.
Okay, so what I'm saying,
It
with
affects
this,
all of
with
them
this,
because you treat the parentheses first, and after that, whatever product you will get from the two parentheses,
Right.
the negative affects
they
all of
multiply
them.
by
Oh, sorry. Oh, does the
negative.
minus sign affect it? Yes, the minus sign is applied to the full product. Yes.
Okay,
That's
that
order
was
of
my question.
operations, right? You do the multiplication before you do the subtraction. Yes, so this minus sign is applied to the full product. Yeah.
I have a question.
Yep.
Rash.
Rash, yep.
Yeah, on the f prime of x, after we differentiated was what we got, okay. Yeah, I see.
Is it okay?
Yeah.
Okay.
Show.
Okay, good. Okay. So I'll say there's another formula called the chain rule. We're not going to do that today. We're not going to do that this semester. We'll probably do it next semester. It's pretty important, but it's a little bit harder than these other ones. So I don't want to do the chain rule yet. But what I do want to do is one of the last very important derivative formulas, and this is something that we talked about last time, was the derivative of sine of x. And if you remember last time, we drew the graph of sine of x, and we tried to write down what the derivative looked like just from looking at the graph. And the derivative looked a lot like cosine. So the last derivation that we're going to do today is we're going to actually calculate the derivative of sine of x using algebra. So if you've been with the program when we've done trigonometry, you may remember the addition formula for sine. So we have an identity here that the sine of A plus B is equal to sine of A cosine of B plus cosine of A sine B. Okay, this is an identity we have for sine. So let's calculate, if we want to calculate the derivative of sine of x, well, we have to use the formula. We have the limit as h goes to 0 of sine of x plus h minus sine of x divided by h. Okay, and what is sine of x plus h? We're going to use this identity. X plus h, it's going to be sine of x cosine h minus cosine of x sine of h. Right, so this is equal to the limit as h approaches 0 of sine of x cosine of h plus cosine of x sine of h, all divided by, and then we subtract sine of x. And this is all divided by h. Remember here, this thing here is sine of x plus h. And again, I'm going to group this into two separate pieces. I'm going to say this is the limit as h approaches 0 of sine of x cosine of h minus sine of x over h. And then plus the limit as h approaches 0 of cosine of x sine of h over h.
I get you.
Sorry.
Yeah.
Okay. All right, so all that I did was I took these two terms and put them in the first one, and then I took this last term here and put it in the second one. And now I have a factor of sine of x. Oh, sorry, this should be an h,
Yes, sir.
not an, this is an h, not an
Yes.
x. Yes, question?
Yeah, there was another bit of clarity. It should be H.
Mm-hmm. Yeah, it should be h. And so I now have a factor of sine of x. I can just pull that out. That has nothing to do with the limit. Right? And I have a factor of cosine of x. I can pull that out. That has nothing to do with the limit. So this is going to be sine of x times the limit as h goes to 0 of cosine of h minus 1 over h, right? Because if I factor out sine of x, I'm left with cosine of h minus 1. And this here is the limit. I'll write it as cosine of x times the limit as h goes to 0 of sine of h over h. And so what we need to do is somehow figure out these two limits. And the problem for both of these is if we just punch in h equals 0, both become 0 over 0, right? Sine of 0 is 0, so 0 over 0. Cosine of 0 is 1, and that becomes, so 1 minus 1 over 0. These are both 0. And so what we're going to do is I'm going to evaluate this limit over here. So the key to figuring out our formula is what is, for instance, the limit as h goes to 0 of sine of h over h. What is this? Okay. Now, people may know that it's 1, but I want to draw you a picture using geometry that shows you why this is 1. Okay, so what is the limit? If we can figure out what these two limits are, then we know the derivative of sine of x is going to be sine of x times this limit plus cosine of x times this limit. So we need to figure out what these limits are. Okay, so the key is what is the limit as h approaches 0 of sine of h over h? All right. Right, so this is what we're seeing. We've seen that in order to calculate the derivative of sine of x, we need to evaluate the limits sine of h over h and cosine of h minus 1 over h. Okay? And so to do this, we're going to do sine of h over h here. And so to do this, I'm going to draw a picture. Okay? So I'm going to draw a picture like this. I have a units. Hello, yes, question?
I thought you were asking your question first. All right.
Oh, no. So what I'm going to do is I'm going to draw the unit circle here. or I'm going to draw just one quadrant of the unit circle. And I'm going to draw an angle here, and this angle is going to be h. And remember, h is in radians. We always measure in radians for doing calculus. And now I'm going to draw two lines. I'm going to draw a line here, and I'm also going to extend this blue line further beyond the circle, and I'm going to draw the vertical line here, right? And this is the unit circle. This is 1. So I want to know what are the lengths of each of these lines. And in fact, this arc of the circle, I'm going to put in another color just so we can contrast. Okay. Okay. So the blue over here is what I've drawn is 1/4 of the unit circle. Okay. So this limit's going to rest on what's the red, what's the green, and what's the purple. Okay, so the first thing to notice is that this is a circle, which means this hypotenuse over here is 1, right? This has length 1 over here. And if you remember your right triangle trigonometry, the sine of h is the opposite side over the hypotenuse. Well, if the hypotenuse is 1, we get that sine of h is equal to the opposite over the hypotenuse, which is equal to the opposite over 1. So sine of h is equal to the opposite side here. And that means that this line has length sine of h. So I'm going to label it sine of h in red. Okay, so this line has length sine of h. Okay.
Hello?
Yes, hello, Rash?
I want to know whether you can use I know they have two type of series, right? Using I know the Markov-Taylor series and the Taylor series, right?
Okay, yes, one can do that, but the way that you derive those is by knowing what the derivative of sine is. You can't use the Maclaurin series unless you know what the derivative of sine is. And so we're trying to figure out what the derivative of sine is. So to use the Maclaurin series is a little bit circular, right? Because you have to know this derivative in order to expand those series in the first place.
Okay.
Yeah.
Okay.
So I'm trying to use only geometry, only pre-calculus. So we're going to figure out exactly what the lengths of all of these segments are. So are people okay with me that the red segment has length sine h? By basing right triangle trigonometry with this right triangle. You have an angle h, that means this side has to be sine of h. Right? Okay, so what about the purple side? Well, the purple side, I have that this over here is 1. I'm going to do right triangle trig on the big triangle. And then I know that the tangent of h is given by the opposite side over the adjacent side. And for this big right triangle, the opposite side is the purple side, and the adjacent side is 1. Right? So this is equal to the opposite side over 1. And so that means tan of h is equal to the opposite side. So this purple side has length tan of h. Right? From using right triangle trigonometry on this triangle. Right? Tangent of h is the opposite side over the adjacent side. The adjacent side just has length 1. This is a unit circle. So the opposite side is just tangent of h. So that's sine of h, that's tangent of h. Now, what about the green arc length? The green arc length is the arc of a circle cut out by an angle of h radians. So you have to remember, so I'll write this down. So green arc length is the arc of unit circle cut out by an angle of h radians. And if you remember what a radian is, a radian tells you the arc length divided by the radius, right? Radian measure equals arc length divided by radius. That's exactly what a radian is. That's the definition of the radian. So in this case, the radius is just 1 because it's a unit circle. So it's arc length over 1. And so that says that the radian measure is equal to the arc length. Well, the radian measure is 8. So that means the radian measure is h. So that means that the arc length also has to be h. Okay. So what we get is that the arc length equals h. Okay, so these are the sizes of all of these lines. We have this smaller vertical line is sine of h. The bigger vertical line is tangent of h. And this arc length over here in between is h. And what we see from this diagram is that sine of h is the shortest. This arc length here is in the middle. And then tangent of h is the longest. So we get an inequality that sine of h is less than h, which is in turn less than tan of h. All right. So are there any questions about how we derived these three lengths? I mean, you need to use some trigonometry for all of them. But we had to have sine of h and tangent of h here. Okay, great. Okay, so if there's no questions, oh wait, I'm going to need another page, right? So what we have is that sine of h is less than h is less than tangent of h, for small h. And so in particular, what do we have here? So sine of h is less than h. So from sine h less than h, we get that sine of h over h is less than 1. Right? Sine of h less than h, we get that sine of h over h is less than 1. And from h is less than tan of h, and remember tan of h is sine of h divided by cosine of h. Tangent is sine divided by cosine. We get that cosine of h times h is less than sine of h. I multiply both sides by sine, and then this implies that cosine of h is less than sine of h over h. Right? I divide both sides by h. So cosine of h is less than sine of h over h is less than 1. So now, what happens? Remember, we're trying to evaluate the limit as h approaches 0 of this thing in the middle. So what happens as h goes to 0? Well, the 1 just stays 1. Well, as h goes to 0, we have cosine of h, this is less than sine of h over h, which is less than 1. As h goes to 0, well, the 1 just stays 1. Cosine of h also goes to 1. Because h is just going to 0, you just get cosine of 0, which is 1. And this thing here is stuck in the middle, which means that this thing here also goes to 1. You can say that it's squeezed between the other two. So if this thing is between these two, and this top one goes to 1, and the bottom one also goes to 1, then this thing in the middle also has to go to 1. So we
So
get as a final, 1 second, what we get here as a final result is that the limit as h goes to 0 of sine of h over h is equal to 1. Question?
yeah,
Rash,
uh,
yep.
I don't know. Is squeezing theory, is that a theory to write? Yeah, I always hear people saying squeezing theorem, squeezing theorem. I don't know
Yeah,
what
it's a
is it.
theorem called the squeeze theorem, but it's kind of, the squeeze theorem is kind of obvious in the sense that like, well, if you're in between two things that both go to the same number, then you're going to have to go to that number also.
Okay, okay.
Yeah. I mean, yes, it has a
Yeah,
name. It has a name. It's called the squeeze theorem.
yeah, hello.
Yes. Who is it? Enoch?
Yes, I just want to like add up to what you said and reply to the comment I just asked a question about squeeze theorem.
Yeah.
Yeah, so brother, it just like for example, if you and me become to be friends, then for example, I have another friend that we have been friends for a long time. Then yourself and my friendship begin to get that closer. Then which means the person I have friend with, you will also be friend with that person. So which means if I'm friend to you and I'm friend to John, it is possible you to also be friend to John. So that's what it means in your simple language.
Yeah, I understand. No, I just want to know the squeezing theory. I understand it. I just want to think about the clarity. Thank
Okay,
you.
bro.
All right, brother.
Okay. All right. So what we get here is that the limit as h approaches 0 of sine of h over h equals 1. This is not an easy limit to do, right? You can't just do a little bit of algebra and get this answer. And you can, if you know L'Hopital's rule, you can't do that either because that requires knowing the derivative of sine, which we don't know yet, right? We're trying to figure out what the derivative of sine is. We're doing all of this nonsense over here to try to figure out what the derivative of sine is going to be. So you actually have to do
Yeah,
something pretty tough. You've got to draw this diagram, show that this h lies between these other two quantities, and then do some algebra. And what you eventually get is that this limit as h approaches 0 of sine h over h is equal to 1. So for
yeah,
matters
yeah,
of
sir.
time, sorry, question?
Yeah,
Yeah, please.
and
Prince,
I want
yes?
to try. I want to plug my phone.
Now
Yeah,
let's
no
go
problem.
back to what theorem where you were discussing about the squeeze stuff.
Yes.
So we'll flip this. Yeah, let's go there.
Yeah, so the squeeze theorem, I mean, I can state it in general if you want.
Okay,
Do-
so
Yeah.
okay, yeah. My question is, when do this squeeze theorem arrive? When do
So the squeeze theorem arrives when you have two functions whose
they
limits
arrive?
are the same.
Is that when? Yeah, actually, when arrive the squeeze theorem?
Oh, when did it
Okay,
was
okay, when?
discovered a long
Very good.
time
So
ago,
it means
right?
if okay, so that means whenever the value of the left hand relates to the value of the right hand becomes same, then it means that the squeeze theorem has to come in the center. Is that what I mean?
Right, yeah. Let me show you graphically, right? So graphically, what do we have with the squeeze theorem? Let's say that I have functions f of x is less than g of x is less than h of x. So let's say and they're all approaching 0. So here's f of x. So f of x, y equals f of, oh, sorry. Let's take this. This is y equals h of x. So y equals h of x up here. And let's say I have y equals f of x down here. And then I have y equals g of x in the middle. So if I have that f is less than g is less than h everywhere, let's say less than or equal to g, less than or equal to h, then if let's say the limit as x approaches 0 of f of x equals the limit as x approaches 0 of h of x, then the limit as x approaches 0 of g of x equals both of these.
Moment, I'm water from what I can.
Oh, right. So here, and the point is what you see here is that g of x is kind of squeezed in between f of x and h of x, right? And so if h and f have the same limit, then the g is going to have to get squeezed in between them. Right here, the limit of h is the same as the limit of f. And so that means if you've got some function in between h and f, then its limit is also going to have to be the same as the other two. right? So if the bottom has the same limit as the top, then the middle one also has to have the same limit. That's what we saw in our case, sine h over h was the middle function. And so that had to have the same limit as the other ones.
Okay,
Okay.
so thank you. Okay, so so for clarity now, for everything to be, if okay, whenever the limit has the if y is equal to h of x has a value of 2 and y is equal to f of x has value of 3. With this the squeeze, a theoretic comes in between.
Yeah, well, the squeeze theorem only applies when they both have the same value. So if limit of f of x
Thank
is
you.
3 and limit of h of x is 3, then the limit of g of x is also 3. Yeah, so
Thank you.
it's just for if they have the same value. Okay.
Okay, well understood. Thank you so much.
Okay, you're welcome. Okay, so the conclusion here is that this limit of sine of h over h as h goes to 0 is actually equal to 1. And this is why radians are important, because we needed radians to make this argument. If h was measured in degrees, we wouldn't be able to have this argument. We couldn't say that this side is h. And so if h is measured in degrees, you don't get this nice limit, and then you don't get a nice formula for the derivative of sine. This is essentially why people use radians. Okay? So I'm not going to do this one. We've had enough proofs for today. It's a lot. I think we're a little tired, but I'm just going to tell you that this comes out to be
Yeah.
0.
So
If
yeah.
you want, sorry.
No, I just wanted to call the answer like is 0.
Oh, 0. Yes. Okay. So
Yeah.
if you want to do this, for instance, you can read this in chapter 1.4 of the textbook if you want to see how this is done. Okay.
Yeah.
But I'll say that this is 0 because I think we've had enough proofs today. So so we get 1 and 0. And so if we go back to, so I'm going to do this, I'll say in book, this is equal to 0, chapter 1.4. And so if you remember what we had that our formula for the derivative of sine of x was sine of x times this limit plus cosine of x times this limit. Well, this limit here is equal to 0. And this limit here is equal to 1. And so in the end, all of this work with the diagrams and the limits and the addition formulas for trigonometry and all of this stuff getting very complicated, in the end, it simplifies to this beautiful formula that the derivative of sine of x is just cosine of x. It's just 0 times sine of x plus 1 times cosine of x. And so this all simplifies down to the derivative of sine of x is equal to cosine of x. Okay, so I'll just write that again because it's an important enough formula. The derivative of sine of x is cosine of x. And it turns out that you can do something similar for cosine, and you get that the derivative of cosine of x is equal to minus sine of x. Okay, so I'm not going to do that. It would be a whole other proof doing the same thing using addition formula for cosine, but in the end, you get a fairly similar formula. So derivative of sine is cosine, and derivative of cosine is minus sine. Okay. And just to review, I mean, you'll see this again in the video and in the notes, but to review, remember what happened. To do the derivative of sine of x, we set up the definition. We had to use the addition formula for sine. Then, after some algebraic simplification, we ended up having to evaluate these two limits. And in order to evaluate this limit, we needed to draw this diagram with the circles and use the squeeze theorem to figure it out. So it's a very sophisticated problem. This result that the derivative of sine is cosine is not an easy result. Okay, this is not obvious. There's a lot that goes into this. Okay, serious trigonometry, both from the kind of algebraic perspective and also from the geometric perspective here. You've got to use both of those. And then you have to know what radians are, and then you have to use the squeeze theorem. So there's a lot that goes into figuring out this derivative. Okay. But in the end, the formula is nice and simple. So in the end, the formula is just the derivative of sine is cosine, the derivative of cosine is negative sine. So now I can answer a question from way back earlier in this class, which is, what is an example of a product rule where we can't use the power rule, where we have to use the product rule? Well, let's say we want to take the derivative of x cubed times sine of x, right? Well, this is a function of the form f of x times g of x, where f
Yeah,
of
yeah.
x, yes, Enoch? Right, so f of x is x
We
cubed
are
and g of x is sine of x. Yeah, so keep going. Yep.
yeah, sure. So now we separately we are going to find f prime of x and multiply by pure g of x.
Right.
Then we add uh pure f of x times g prime of x. So that is
Exactly. Right. So
okay.
let me just stop you for a second. I'm just going to remind everybody that this is the product rule. So keep going. Yep.
Yeah, so now and we know that f prime of x is 3s squared, which is
Mhm.
3s squared times sine of x, which is 3s squared sine x
Mhm.
plus we know that g prime of x will be cosine x and pure f of x is just s cubed, so we'll get s cubed times cosine x.
Great.
Yeah.
There you go.
And if we let we factor out x squared.
Yeah. So if we like, we can factor out x squared, which will leave us with x squared times 3 sine x plus x cosine of x. Great. Both of these are the same.
Well, you're
Right? You
asking
can
you
factor out x squared.
so you're asking you to simplify, right? That was an example.
Yeah. So this is an example where you have to use the product rule. There's no way, because you've got a sign, there's no way that you'll just be able to use the power rule here. You have to use the product rule in order to get this formula. You got to have f prime g plus f g prime.
Sure.
Yeah, my concern.
Yes, question.
Yeah, please. Yeah,
Mhm.
we have that g prime of x, and how
Mhm.
can g prime of x become cos x?
That's exactly what we did, right? Remember the derivative, this is the same as prime. They all just mean the derivative. They all mean the same thing. So this is what we just
Okay,
did. We showed that the derivative of sine is cosine. So
it's
anytime we need
cosine.
to
Okay,
take a derivative of sine, we get cosine. And anytime we need to take a derivative of cosine, we get minus sine.
okay.
Right.
Thank you.
So that's it. So that's why we have that the G prime, again, I'll label these all. This is, F prime, this is G, this is F, and this is G prime. Okay. Okay, so this is a product rule example where we need to use the product rule and knowing what the derivative of sine is. Okay, so we're just about out of time. I want to do one more example. So I'm using another notation for derivative, y prime, but remember, this just means the derivative. So what we're saying is, what's the derivative of tangent? Well, if we remember, tangent of x is equal to sine of x divided by cosine of x, right? So the
So
derivative of,
that
yes. Mm-hmm.
yes, so that would just be secant square of x.
Right, but we're going to derive this, right?
Yeah,
So, yeah. Mm-hmm. So we
yeah,
use the,
we can do it. So for this one, since we have tangent of x is equal to sine x over cosine x, we will use a quotient rule
mm-hmm.
where we find the derivative of the numerator and multiply by the denominator, and also find the derivative of the denominator and multiply by that of the numerator and divide by the square of the denominator.
Exactly. So this is the quotient rule over here. F is the numerator, G is the denominator. We get this formula. And because we know the derivatives of sine and cosine, we can do this. So what do we get,
Yeah, so we'll have it to be equal to square x.
Yeah, so G is cosine of x. Yep.
Yeah, so we'll have so which means cosine of x times cosine of x, and just cutting it short to say cosine square x.
Right. So cosine of x, I'll just write out
Yeah.
each part. So that's f prime.
Okay.
Remember the derivative of sine is cosine. Great.
So minus.
Mm-hmm.
Okay, so you have negative sine x times sine x.
Right. So sine of x, this is the f part
Sine.
here. And then
Yeah.
negative sine of
Tan negative.
x is the
Yeah,
g prime.
all
Right?
divided by cosine squared of x.
Exactly. Great.
So now we know that
Just
cosine
before
x
we
tan
move on, I just want to remind everybody, right? How do we get this? The derivative of g, that's the derivative of cosine x. We have that from our previous page. That's negative sine x. Okay, continue.
Yeah, so we know that cosine x tan cosine x is cosine square x.
Mhm.
And we know that sine x tan sine x is sine square x. But we know that negative tan negative is positive, so we'll get sine square x all divided by cosine square x.
Right.
Yeah, and now we know that from the Pythagorean theorem, we get a cosine square x plus sine square x is equal to 1. So
Right.
we will have 1 all divided by cosine square x.
Mhm.
And we know that the, 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 the inverse property is just cosine square x is just secant square x. Okay, so yeah, so it's the inverse property of that. So that's it.
Perfect.
So,
Great.
hello?
Yes, Rash?
Yeah, but you can use the first principle to right to get first principle.
Mm-hmm.
Yeah,
You
you
use the
can
first.
Yeah, if you want to go from the definition, you could probably figure this out also. But the point is, once we've done sine from the definition and cosine from the definition, it's much easier to now do everything in terms of the quotient rule.
What? Oh, I say you can use the principle, the first principle too, right?
Yeah, you
Okay.
can. But you'd need to then use the addition formulas for tangent, and things would get pretty complicated.
When you use that, I think we get something. I know.
Yeah, I mean, it will work, but it's harder than this.
Okay.
Yeah.
For the first principle, that.
Yeah, for the first principle, yeah. Okay, so this is it, right? So because you know that you can use the quotient rule, because you know the derivative of sine and the derivative of cosine, you can use the quotient rule and simplify everything, and you end up getting that the derivative of tangent of x is secant squared x. I'll just rewrite this, and then we'll be done because we're out of time. So the derivative of tangent of x is actually equal to secant squared of x. Okay? So that's how this works with the quotient rule. Okay, so today,
Yeah,
just
so,
yes, question or comment?
yeah, that about will we do it up to cotangent x or cosecant
Yes,
x?
this is homework number 1.
Oh, yeah.
Okay. So,
Oh,
yeah.
that's
So,
it. They are very simple. Yeah.
yeah. So, okay. So, what have we learned today? We did the product rule, the quotient rule, and we learned how to calculate the derivatives of trig functions, or at least of sine and cosine, and then this tangent. So the good news is once you know the derivative of sine, you don't have to really recall this derivation. But I think it's good to see it once. If you want to say that you're a mathematician, you should have seen how these things go, right? So so that's why I wanted to do one time in detail how to really calculate the derivative of sine. Okay, but now you have a much larger library of functions you can take the derivative of. So in the homework, we have a few of these. So the homework is first calculate the derivatives of cotangent of x and secant of x using the quotient rule. And just remember that cotangent is cosine divided by sine, and secant is 1 divided by cosine. Okay, so these will be, you can just use the quotient rule as we wrote down for all of these, and you can come up with an answer. Second one is, can you find the derivative of x sine of x divided by 3x plus 4? This is a little bit harder because it's a quotient rule, but then when you take the derivative of the numerator, you have to do a product rule there. So I'll let you spend a little time on that. And then question 3 is, suppose that we have two functions that are differentiable at x equals 5, with f of 5 equals 1, f prime of 5 equals 6, g of 5 equals minus 3, and g prime of 5 equals 2, then can you calculate the derivatives of f of x times g of x and f of x divided by g of x at x equals 5? So you're going to need, again, here to use the product and the quotient rules.
Doctor, please.
Yes, Rash?
My homework, the exercise parameter also do.
Yes, I'm going to send these on the chat. Yeah,
So
I'm going to.
You're explaining something, so I will not getting it clear because
Oh, I was just reading the exercises.
Okay.
I was just reading them. Okay. So on the chat, we'll have this. And so next time, which is the last week of the semester, we're going to apply. So today was pretty theoretical, right? We did a lot of proofs. So next time is going to be applications. We're going to apply differentiation to optimization problems, and I would say this is the most important application of calculus. Okay, this is the most important application of calculus, is what do derivatives do? They help you maximize things and they help you minimize things. Okay, so we're going to spend the whole time thinking about this kind of optimization, which is kind of like partly is the reason calculus was invented, to be able to do these things. Okay. So, and that is going to be the last class of this semester, and then we're going to resume again next in January. Okay. Um, so any questions about anything from today?
Hello? Yeah,
Hello.
hello?
Yes. Yes, Enoch.
Yeah, I'm still figuring out this number three. I'm not understanding. Or this f of x or f of 5 equal 1, was it a function that you place in a value of 5 to get 1?
Exactly. So f and g are functions. I'm not going to tell you what functions they are. I'm just going to give
Okay.
you a little bit of information about the functions. So I'm just going to tell you that this is the value of f at 5 when you plug in 5. This is the value of f prime when you plug in 5.
But
This is
but
the
but
value of
that
g.
if
Yeah.
you do the setup, it just if you do the setup, you definitely understand that direct replacement, and then
Yeah.
you do carry on with the function.
Yeah, you can, it works. Yeah, the problem
Okay,
works. I just don't have to
so
tell you what the function is. Yeah.
yeah, so we are coming up with a function, right?
You don't have to come up with a function. You can answer this
Already
question
there.
without coming up with a function.
Oh,
So
okay,
you
okay,
just need to know what the derivatives are at 5. So you only need to know what these things are here at 5.
okay,
Yeah.
okay,
Yeah, you don't, I mean, you can come up with a function if you want, but you don't have to. It's not really part of the problem.
okay.
Okay. Other questions? Okay, so as always, I'll be sending out the notes later today and the recording later today. I'm sorry everything was a little bit late today, but I think we were able to finish everything up. Thank you, Sange, as always, for getting everything out. And thank you again every week for showing up and paying attention. So great. So I hope everyone has a nice weekend, and I'll talk to you all next week.
Hello,
Hi,
hello,
Abraham.
Andrew.
Abraham, yes.
Yeah, thank you very much for today's class. We
Mhm.
hope to see on the 20th. I know it will be the last day for the semester.
Mhm.
We are still waiting for the minister to very sign that document.
Oh, really? Oh, it hasn't been
If the
signed
minister,
yet? Okay.
yeah, yeah, if the minister sign,
Yeah.
then we'll be able to reach to you.
Okay. But you
Sanjay
have
will
them,
just
right?
Hello.
Yeah.
no,
Hello.
Hello,
she just coming.
Sanjay?
Yeah,
Sanjay?
yeah,
Hello.
Hello? Yeah, Sanjay?
yeah. Hello.
Yeah, yeah. I will get to you next week regarding the. I the one who got to follow up regarding the certification. And I'm sorry today. I went on the field and I left the card here, so I have to come back to distribute the food. It was late today.
Okay.
Sorry. Okay.
Yeah, those who did not receive that data today, they will be received it next week. Maybe you want to double it straight next week for them.
Well, I will be the minister and will tell you. I will call. I will write to you. I mean, call you and tell you.
Okay, okay, okay. Thank you. Thank you,
Okay.
Andrew.
Okay, you're welcome.
Okay. Thank you for the day.
All right, you're welcome, everybody. And Sanjay and Abraham, I'll get you the attendance list later today.
Okay. Yeah,
Okay, thank
I
you.
tried. Yeah, my computer been gave me some problem, but I hopefully by the weekend I will try to see how I can send the reports.
Mhm. And to everybody
Okay.
here, please type your name in if you didn't do that already,
Mama.
because I'm gonna close the chat soon. So I think Rash, did you write anything? I'm just gonna write your name to make sure we don't miss you. Okay. Okay, so have a nice weekend, everybody, and I'll talk to you next week. All right. Talk to you soon.